Welcome to our Interpretable Machine Learning lecture. My name is Ben Bischel, and in this session here we'll talk about generalized linear models. And today I'm also wearing glasses, so I can actually read the slides on our teleprompter and do not have to guess what's on them. So in this session here, we'll give a brief, rough summary what generalized linear models are from a statistical perspective, how they would also be used in a classical statistical course, and then we'll use the logistic regression as our main example, discuss this a little bit more in detail, and we'll mainly focus on, at the end, on how to interpret a logistic regression model. You will see that this is slightly more complicated than interpreting a standard linear model, but still very possible. So we still have p-values for the importance of certain features, whether they are significant or not. And we will also see that we can interpret the coefficients, or let's say the exp of the coefficient, so the exponential function of our coefficient as the factor, how the log odds change when we increase that specific feature by 1 unit. But I guess let's do that on the slides. So what's the generalized linear model? So assume we have a target variable which is not necessarily continuous, how we assume that in a normal regression. Also, it's not necessarily normally distributed. So in that case, our traditional linear model is not suitable anymore. Examples for popular scenarios which deviate from that are, of course, where the target variable is binary. So maybe we do some form of disease classification, and then we would assume something like a Bernoulli distribution for our outcomes, and then that gives directly rise to our logistic regression model. And you know that these binary outcomes are paramount. I guess many machine learning models are introduced for these scenarios anyway, but specifically the interpretable logistic regression model is then also extremely popular in areas like medicine, where they are used to model, for example, the classification of a certain disease or the efficiency of a certain intervention or so on. Then there are also count variables. For example, we might want to model the number of sold products, and then the associated distribution for that would be a Poisson distribution. Or even more complicated, we do time to event modeling, so survival models, and then often the outcome is something like time until death for certain really bad diseases, again in medicine maybe, and then we would assume something like gamma distribution. I will not really go into these two more complicated model classes here. In this session, I will mainly focus on the logistic regression model. So how do we now define a GLM? So this is not that difficult. So we will still use something like a linear score. So I'll use that x transposed times theta, but we will now say that our expectation of y given x is modeled by our linear score when we push that inside of this inverse link function here. So we allow ourselves this g guy here to somehow transform our linear score to the appropriate outcome scale. Okay. Now, of course, we need to specify this link function, and we need to specify which distribution we want to work on. As for the linear model, if we want to work with higher order effects, if we want to work with interaction effects, we have to manually specify them or do something extra, like some extra feature selection procedure on top of this model. And of course, the interpretation of the weights will now depend on the link function and the assumed distribution and how that works, and that this will become slightly more complicated than for the regular linear model we'll exactly study now in the case of logistic regression. So, let's take a direct look at that. So how does our logistic regression model work? So this is what we would call a generalized linear model with a Bernoulli distribution. So Bernoulli distribution is basically our outcome is like it's a 0-1 variable, so it's a binary variable, and it kind of behaves like a stochastic coin flip, right? There's a probability of the outcome being 1 and the probability of the outcome being 0. So there's a probability we are modeling for the positive class, and 1 minus that guy would be the probability of the negative class. I will not now go super slowly about all of the details of such a model. Please do that by referring to the literature or going to a more in-depth course on logistic regression. Here, we now want to briefly summarize that and have a look then at the interpretation of the coefficients. So how does our link function look like? So this is not that difficult. So what we will use, so if I would explain this more from a machine learning perspective, what I have to do now is I have this score here, so theta transpose times x, that's my linear score, and I still want to kind of work with that because I like that linear structure. Now that score, if I compute that, that goes from, well, that lives on this real line here, and it goes from -inf to +inf. And the idea is that if we compute for a certain observation x, a very high value here, that would be a very high confidence for our x belonging to class 1. And if we have a very small negative value, well, or in terms of its very small value, or let's say a very negative value, yeah, something like -100, -1,000, -10,000, this would be very high confidence for it not belonging to the positive class, which means very high confidence for it belonging to the negative class. Now, obviously, we want to somehow transform this into a proper probability, so we somehow have to transform this complete real line, which goes from -inf to +inf, to a probability between 0 and 1. And we do that by applying this guy here. And some people call that the logic link function. I guess people who are more from statistics, other people call this a sigmoidal function. This is a class of functions which has like an S shape, and you see the plotted function down here, right? It looks a little bit like an S. Okay, or some people also call it a logistic transfer function. This is usually how this is called also in neural networks, where this is also used for modeling binary outcomes, but it's also used in neurons as a transfer function there. Now, so how does a logistic regression model work? We now compute these linear scores, but then we do one extra step. We push these linear scores into this transfer function guy here, and this then will form all of our, let's say, confidence scores or linear scores from -inf to +infs to something in the interval between 0 and 1. So very negative numbers will be transformed into probabilities close to 0 for the positive class, which means nearly 1 probability for the example belonging to the class. Values close to 0 will be transformed to a score of approximately 50% for the positive class, and therefore also about 50% for the negative class, so we are not really sure. And extremely large positive values will be transformed to a nearly 100% probability for the observation belonging to the positive class. And if you want to visualize that now with two features, it would look like this. Yeah? So you have this x1 and this x2 here, and then you see this, I don't know, kind of distorted piece of paper here. I guess you can kind of mentally envision it like that, where you have this S-shaped function going on here like this, right? So you compute the score, and then you go into the transfer function, and this is how the prediction surface would look like for a logistic regression model based on two features. And I will not go into how this model is fitted. You can do this by with some numerical method like gradient descent, or you can do something smarter like BFGS or whatever. So it's not a particularly difficult problem in terms of optimization. It's convex, and there are different methods we could resort to, but it's not analytically solvable anymore as the linear regression model is. So the next thing we can discuss a bit is how do we now transform these probabilities into concrete classes. So the usual idea is to set a certain threshold, and what we're doing here in logistic regression is not really particular to logistic regression. Usually we do this for any form of probabilistic classifier. So we pick a threshold. If we don't have any further information or regarding the evaluation and the application of that model, very often we do that at the 50% threshold. So every posterior probability for x belonging to class 1, if that's larger than 50%, we usually classify it as class 1, and if it's smaller, we classify it as class 0 or -1. And if you now analyze the logistic regression model with a little bit of extra math, so I guess maybe 2 lines, which I will not write down here in this session, you can easily figure out that this logistic regression model will only give rise to a linear classifier, okay? So your decision boundary, yeah, which separates the positive from the negative class, will always look like that. So it will be a hyperplane in a p-dimensional space if you have p features. More you cannot model with the logistic regression model. You can make it model nonlinear decision boundaries in your original feature space if you introduce extracted features, right? If you use interaction or higher order effects, and if you introduce them manually into the model, then you are still going to be linear in this derived space, but you can become nonlinear in the original feature space. Okay, more important to us here, how can we now interpret such a model? This is slightly more complicated. So in the usual regular linear model, if we look at our coefficient for a certain feature, and if we now increase that feature by 1 unit, we know that our outcome will go up coefficient points. Yeah? Now, this will not work for logistic regression. It's pretty obvious, right? If we take our outcome as the probability, the positive probability, then, well, I mean, if we increase a certain feature for 1 unit and another unit, and then this probability would go up in a linear fashion, at some point would go beyond 100%, that doesn't make sense, right? So we have to do something slightly different here. So first of all, it's usually easier to interpret the logistic regression model and its coefficients if we think in odds. So odds is the ratio of two probabilities. So here, for a certain observation X, we'll now look at the probability of it being class 1 divided by the probability of it belonging to class 0. So here we have the probability of it being positive divided by the counter probability. So let's maybe compute a simple example here. So maybe we know that pi of x equals 0.05. Then we know that our odds are, well, 0.05, which is the same as 3/4, divided by the counter probability, which now must be 0.25. So this is 2/4. So if we like to think in odds instead of probabilities, we would say, hey, it's actually 3:1. So the odds are 3:1 that our observation X belongs to the positive class. Now, unfortunately, it's a little bit more complicated because it turns out that we really would like to exploit the linear structure of our model here. And yeah, if we can't really associate our linear predictor or the linear part of our logistic regression model, which is this guy here, with the odds, but it turns out if we are willing to take the log odds, right, then the log odds of our model are exactly this linear predictor here, okay? So we can now say, in terms of interpretation, we can now reuse what we have learned about the linear model. Changing our feature xj by 1 unit changes our log odds, where we compare the probability of class 1 to the probability of class 0 by theta j points, okay, by coefficient j points. Now, this is technically correct, but I guess most of us don't really like to think in log odds. So we now go one further step. So what we are now also going to do is that if we what we can also do is we can basically take a look at the odds ratios. So first of all, what we can say that the odds here, okay, if the log odds can be written in this linear form, we can say that our odds here can be written as x of this linear form, okay? And if we now mainly are interested in what happens if we increase a certain feature, a given feature under consideration, xj, by 1 unit, we can now compare how these odds change, okay? And in terms of a multiplicative factor, because this now will work nicely together with this x of linear score structure, okay? So here we say, hey, let's take a look at the odds. Well, let's maybe take a look at this guy first. So these are just the odds of our current model, maybe at a certain observation. And now we change, for a given feature, the value of that feature exactly by 1 unit. And we are now interested in how do the odds change as a multiplicative factor. So we divide these two guys because that exactly gives us this factor. And if we now divide this exp of linear term here on the top by where we have increased xj by 1 point, and we divide that by the original odds, then basically nearly everything cancels out except for this part here, and we see that the result of this is simply exp of theta j. Now this gives finally rise to our interpretation of the logistic regression model. So if we change xj by 1 unit, this changes the odds ratio. So this changes our odds. We could also say this changes our odds by the factor exp of theta j. And that is useful, and I guess people can remember that and can apply that in practice and associate something concrete with that. So let's finally do that for a concrete example. So here we're taking again a look at our bike sharing data set. Yeah, that's a regression problem. So we are cheating here a little bit to still be able to apply this. So we'll now convert this into binary classification problems. So we'll just say if the number of bike rentals is high, which we here define as a 70% quantile, doesn't really matter that much, then we'll define our outcome as class 1. And if the number of rented bikes is low for a given day, so if it's below this 70% quantile, then we'll define the outcome as class 0. So we are just like simply binarizing our numerical outcome. Yeah, so it's probably nothing I would really do if I would in applied work when I work on the data set, but we just kind of wanted to reuse the data set here as a toy example, okay? Now we can fit a logistic regression model to this. And what you will now see here are the coefficients. So you see this weight column here, these are our coefficients. We see the standard errors and we see the p-values. So the p-values we can interpret in a similar manner as for the linear model. I will not go into this here, but I want to now give a more concrete example how we can interpret the coefficients. So let's now take a look at temperature, okay? So for temperature, we have a pretty low p-value. So hopefully we can say that this feature is influential. At least we, for here, I now want to assume that, and I guess we can also, there's not a lot of counter evidence for that position in the data. And we now take a look at our coefficient here, and our coefficient for temperature is approximately 0.3. So if we do exp of 0.3, this gives us approximately 1.3, okay? So this is now our multiplicative factor, how our odds change when we increase temperature by 1 unit, which in our case here is 1 degree Celsius. So if the temperature rises by 1 Celsius, this is how our odds change when we compare the probabilities of the number of bike rentals being high compared to the number of bike rentals being low. So maybe let's make this very concrete. Let's say we are at a current observation X and our probability for the positive class, so for the number of bike rentals being high, is 0.05 as we had before. So we already computed before that then our odds are 3 to 1, right? Did that before. Now, how do our odds change when we change our temperature by 1 degree Celsius? Then we have x of theta, well, I guess I can say theta temp maybe. That's roughly 1.3. So we now have to multiply our odds by that factor. And if the odds are 3 to 1, our new odds will be, well, 4 to 1, because 3 times 1.3 is approximately 4. So our new odds would be 4 to 1. Well, I guess I should maybe not also write that behind my back. Always doing the same mistake. So let me maybe try this again here. This was a little bit stupid. So our temperature rises by 1 degree. So maybe let me write here. So we now remember that our odds For that specific case, we're 3 to 1. So our new odds are 1.3 times the old odds, which would be approximately 4 to 1. So if our odds are 4 to 1, what does that mean in terms of probabilities? So our new probability would now be, hopefully you can now do that in your head. If it's 4 to 1, this means we have a probability of x belonging to the positive class of 80% and probability of it belonging to the negative class as 20%, right? Okay, so we have like 4 parts of weight, yeah, confidence weight of it belonging to the positive class, and one like part of it belonging to the negative class, so in total 5. So if the odds are 4 to 1, it's 80% to 20%. And this is how you can think about this, right? So unfortunately, you can't really use that multiplicative factor to understand how your probabilities change, but you can use it to understand how your odds will change, and then you can still transfer at the end odds to probabilities. So this puts it until here. I guess I went a little bit more into details anyway than I wanted to, but yeah, I hope you enjoyed that and it was useful for you. Bye bye.